Hi everybody. This video is going to be on section 10.6, which is called the unit step function. Okay. So just to describe what we are working up to in 10.7, we now begin the process of learning quick techniques for finding the Laplace transform of piecewise continuous functions. Okay, so the idea is that in nature and engineering, a lot of times we want to symbolize functions that sort of turn on and off or that become something else abruptly, and we want to be able to find the Laplace transform of such functions without having to resort to the definition of Laplace transform every time, right? So it's been nice that we haven't had to deal with those integrals in a while. So we want to continue to be able to avoid the use of those integrals. And we do that by developing some theorems and all that stuff. Okay, but to do this, we first need a definition. So the unit step function which we write it as UA of t is defined by the following. UA of t is equal to 0 when t is between 0 and a, and 1 when t is greater than or equal to a. Okay, what is a? A is any positive constant. Okay, any positive constant. A is not allowed to be 0, okay? So what does this mean? This means that if you were to draw a sketch, well, let me do that here. So let's say that we were going to draw UA of t. If this is 1 and this is a, what we're saying is that the function is 0 until we reach a, and then at a, the function becomes 1. Right? It's a very simple function. And what does UA of t model? So you could think of UA of t, it models a switch being turned on, right? Being turned on at t equals a. So if you think of t as time, it's like at a seconds, whatever a happens to be, the switch is turned on. Okay, so that's what this models. Now, it doesn't seem like we can do much with this function, but actually we're going to see that this function is going to unlock the ability to write any piecewise function in this notation. But to do this, first, I want us to see what happens when you subtract two of them. So what happens when you calculate UA of t minus UB of t for A smaller than B. So what happens if you take one of these guys and you subtract the other away? Well, I'm going to illustrate this in an example. So for this example, we're going to do something very simple. I want us to sketch the following. F of t is equal to u1 of t minus u3 of t. So what happens if we subtract these two things? Now, the important thing here is to notice that there are really three cases going on, right? Because we have a 1 and a 3 in there, we know that we're going to have three cases. Either t is smaller than 1, t is between 1 and 3, and t is larger than 3, right? So let's see what the three cases are. First, what happens when t is smaller than 1? When t is smaller than 1, both of these values are 0, right? So you end up with 0 minus 0, which is 0. So it's 0 when t is smaller than 1. Now, because we're dealing with t's that are actually at least 0, there's no harm in writing it this way. Okay, just because we're not talking about inputs of t that are less than that, okay? Now, what happens when t is between 1 and 3? Well, when t is between 1 and 3, that actually makes the first guy 1, but the second one 0. So you get 1 minus 0, which is 1. So it's 1 when t is between 1 and 3. And then what happens when t is larger than 3? If t is larger than 3, then that means they both become 1. So 1 minus 1 is 0, so it goes back to 0. Okay? So then, how would we sketch this? It's quite simple, right? If we have 1, 2, 3, and we keep going, and then this is 1, I'm going to use red actually, so what does this emulate? This emulates turning a switch on and then turning it back off, right? So it's like we turned the switch on at t equals 1, and then we turned it off at t equals 3, right? So this was so we turned it on at t equals 1, right? And then you could see that the switch was turned off at t equals 3. So this idea of turning it on and turning it off was exactly described by this subtraction, right? So this is how we want to view it, okay? I want us to notice that when we had f of t equals u1 of t minus u3 of t, and then there wasn't a 1 written there, but I wrote it as a 1. Here's how you want to think about it, okay? This first number is the time it turns on. This number right here is the time it turns off. And then this number that it's being multiplied by, or this function I should say, this is the function being turned on. Or off. Okay, now in this example it was quite easy because we were just turning the function 1 on and off, right? Because there was nothing written there, right? In our original example, you could see that there was nothing here, so it's like there was a 1 there being multiplied. So I'm hoping that you guys can see what's going on here. What this leads to is that we can express every piecewise continuous function as a combination of unit step functions. Okay? The idea is that you would take UA of t minus UB of t, and then you would have some function which we can call, fi of t, whichever function that we're turning on at that step. And so you could just keep doing this, right? Each function that you want to turn on and off at a particular time can be done this way. Okay? So what I want us to do now is actually practice the notation here. Okay? We're not going to learn how to do Laplace of this in this section. That we're saving for the next section. All right? But let's actually practice taking a piecewise function and expressing it using this notation. So, example. Express the following function in terms of the unit step function. And this function is going to be f of t is equal to, starts off with 0 when t is between 0 and 1, t minus 1 when t is between 1 and 2, and then 1 when t is at least 2. So how do we analyze these three parts? And you just want to look at it as three parts, okay? Now, when starting off with 0, when you're 0, nothing has turned on yet, right? So let's just say here, I'll just say nothing is on, so that you don't have to really worry about this part, okay? So what about this part? This part, you're turning on t minus 1 at t equals 1, and then you're turning it off at t equals 2. So what are you going to get? The way you're going to write it is like this. u1 of t minus u2 of t, right? Because it's being turned on at 1, turned off at 2. And you're going to multiply that whole thing by the function t minus 1. Okay, because that's when it goes on and that's when it turns off, okay? What about this one? For this one, you're turning on the function 1 at t equals 2, but then you're never turning it off, right? So the way you would write it is like this. u2 of t, and I'll put a 1 here just to note that I did take it into account, but of course it's not going to matter. So because we got the following three pieces, you just add all three together, okay? So this means that f of t is equal to, it's going to be u1 of t minus u2 of t times t t minus 1, and then plus u2 of t times 1, okay? Now, you could write your answer this way because technically it just said it just wanted us to write it in terms of the unit step function, okay? But this is going to give us the answer, right? Now, I want us to also rewrite it in a slightly different way, okay? You're going to find out why in the next section because we're going to learn the second shifting theorem, which is what allows us to take the Laplace of unit step functions. And for those, it actually is easier if we have each unit step function isolated from the other. So rewriting in the form rewriting in this form where you have each unit step function individually times the function that you're turning on and off there, this makes taking the Laplace transform easier in the next section. So the answer is better written as, so here's how you can write it instead. What you can do is just algebraically distribute, right? We can distribute everything here and combine like terms, okay? So, take this guy and distribute it with this guy, and then combine like terms. So this is what it would be, right? You have your u1 of t first, and what's that being multiplied? It's being multiplied by t minus 1. And then when you have u2 of t, what's that being multiplied by? Well, you have a negative in front of it, so it's negative t plus 1, but then you're adding another 1 to it because of this guy on the right, and so that becomes times 2 minus t. So this is, I'll call this the Laplace-friendly way of, writing it down, okay? This equivalent answer is what we just got. And actually, we will make further adjustments to this after we learn the theorem in the next section. But this is good practice, okay? I want you guys to practice the algebra here. It's really not that bad. We're just combining like terms here and factoring out the ui's of t, right? The answers are equivalent though, okay? There is one thing I want to say, which is, so note, and this will apply in the next example that I do, since A must be positive in ua of t, we use 1 instead of u0 of t if a function starts off. Oh, let me not write starts off. It's a little confusing, my terminology. If a function begins turned on. Now, what do I mean by begins? I mean at t equals 0, okay? So what I'm saying here is if we start off at 0 with a function turned on, then instead of saying u0 of t for turning it on at t equals 0, we're just going to use the number 1. this is equivalent if we assume that t is at least 0 anyway, right? We don't need to say turn it on at 0 because there's nothing before 0 anyway. We're sort of visualizing our time as beginning at 0, so we're never going to be putting in negatives into our function. Okay, so this next example is going to be fun because we get to do a more complicated piecewise function, and you're going to see just how nice the unit step function is. Okay, so we're going to let f of t be the following piecewise function. We have t if t is between 0 and 2, -1 if t is between 2 and 4. And we're going to need a little more space here. And t minus 4 if t is between 4 and 5. And then e to the 5 minus t if t is greater than or equal to 5. Okay? So we've got this complicated piecewise function here. Part A is going to be to sketch f of t, and part B is going to be to express f of t in terms of the unit step function. Okay, so this isn't going to be too bad. Let's start with our sketch, okay? This will be the fun part, right? We want to do this sketch, and I want us to think about what's happening here. So we begin the problem with turning the function on at 0, and it's going to be the function t. So let me go ahead and sort of draw this out here. So we've got 1, 2, we've got -1, and we've got 1, 2, 3, 4, 5, and then stuff happens after that, but this will be enough, okay? So remember, it's the function began with t when t is between 0 and 2, and so we began. That has a slope of 1, and so it looks like this, and we're going to go to the point 1, 1 here, but it does not include that, so I'm going to leave a little open circle there. Okay, next, we are at a constant -1 between 2 and 4, so there's 2 and there's 4, and we're at -1 the entire time, and I believe it starts with equal and then does not equal, right? So it looks like that. Next, t minus 4, that's really like the line y equals x except shifted to the right 4 spaces, and it starts from 4 to 5, so actually it's going to go from here to here. And then finally, e to the 5 minus t, that's the same as e to the negative t minus 5. So think about it this way, right? E to the negative t is like e to the x, but it goes down and to the right, except it's shifted to the right 4 or 5 spaces, so that means that it actually crosses right here and then goes this way. It's going to go forever approaching there, right? So as you could see right there that if you were to plug in 5, you actually get 1 into the function, right? Okay, so that's what this function looks like. A little bit wacky. We're turning on this constant, this linear function, and then it turns off, and then we have a -1, and then all that stuff, okay? So that's our part A. This is what we're doing. We're looking at this function, and now we want to express f of t in terms of the unit step function. So let's go back to our definition here. Let's think about this. We are turning it on at 0, but remember I said instead of using u0 of t, we're going to use 1. So turn it on from the beginning, and then turn it off at 2, and the function that we're doing this to is t. You know what? Let me do this in red so we can see it, okay? See it a little better, okay? So again, we're doing 1 minus u2 of t, and we're doing this to the function t. Next, we're turning on at 2, and we're turning off at 4, and the function is negative 1. Next, we're turning on at 4 and we're turning off at 5, and the function is t minus 4. And then finally here, we're turning on at 5 and we're never turning it off, so it's just going to be u5 of t and then e to the 5 minus t. Okay. So then we add all of the above together and we get the following. So this is for part B. We get f of t is equal to, so what do we get first? So think about it. I'm actually going to distribute over here. Let me get a different color here. Let me use blue. So I'm going to distribute this guy first to both of these. So then here's what I get. I get t and then plus, so here's u2 of t. And what am I going to have? What's the coefficient of u2 of t? I'm going to have a negative t from that top, but then I have another negative 1 from here, so it's going to be negative t minus 1, right? Okay, next, I'm going to have u4 of t, and I get something from that and something from this, right? So it's going to be a positive 1, and then I have plus t minus 4. That becomes t minus 3, doesn't it? Okay, so it's going to be u4 of t times t minus 3. Next, I have a u5 of t. And what do I have? I have this guy, but then I also have the e to the 5 minus t term, right, on the bottom. So what's that going to be? Well, I have a minus in front of the u5 up there, so that's actually 4 minus t, if you apply the negative to it, but then plus e to the 5 minus t, so it's going to look like this, multiplied by 4 minus t plus e to the 4 minus t. Let me, this looks a little messy. Let me write it on the next line here just because I ran out of space. So this is going to be plus u5 of t times, again, it's going to be 4 minus t plus e to the 5 minus t. Okay. Again, we are going to learn how to simplify this further because this is still not in complete Laplace-friendly term. There is one little adjustment that we're going to have to make, but we're going to save that for the following section because that's where we're actually going to learn what we call the second shifting theorem, and we're going to learn how to take the Laplace of something like this. All right, guys, that's it. Thank you so much for watching.